I'm Gary Barnhart. I'm the Executive Director of the National Space Society. Without further ado, I would like to introduce the first speaker, Mark Hopkins, who's the Chair of the Executive Committee for the National Space Society. Mark has been an officer of the National Space Society for 28 of the last 34 years. He holds degrees in economics from Harvard and the California Institute of Technology. He is also a former RAND Corporation economist. Mark?
All right, this press conference is going to be dedicated to space solar power in general, and specifically the International Academy of Astronautics report, which has just come out. And just give a little commercial here about the National Space Society. We're the world's leading advocacy organization for the human space program. We were created in 1987 by a merger of two earlier organizations, one of which was founded by Wernher von Braun in 1974. We have a number of items that are of particular note. Our Ad Astra magazine is award-winning. We've got 50 chapters scattered around all over the world. We do the International Space Development Conference once a year, which is fairly famous at this point. We've been doing it for over 30 years. The next one will be in Washington, D.C. in May. And we've had a number of illustrious people which have been associated with us in the past. One is our just prior to the current executive director, George Whitesides, who left in 2009 to become the chief of staff at NASA and is now CEO and president of Virgin Galactic. Also, Lori Garver was once our executive director. She is now a deputy administrator at NASA. And without further ado, let me add a couple of acknowledgments here. Our co-sponsor is Space Canada. The president is George Dietrich, who will be talking to us later. And they provided generous financial support. And we also got a personal donation from Dale Scran. Let me give a very brief overall description of space solar power. There are numerous options for doing this, which is one of its strengths, because if one option doesn't work out, then we can go to a different option, and that might work. In the report itself, there are 3 options which are considered in detail, and 10 other options which are considered in less detail, and there are more options beyond that. For the purpose of my discussion, which is not the same as John's discussion, which will be coming up later, let's take what I'll call the base case. And this is simply an array of solar cells in space which gather electricity, and that's converted into a microwave beam which is transmitted to the Earth and then converted back into electricity and fed into the power grid, just as the power produced by any power plant is. The advantage of space solar power as compared to ground-based solar power is 2 major things. One, the amount of energy per unit area in space is about 7 times greater than it is on the ground. And also, you can send the beam down to Earth continuously, and hence you avoid the problem that ground-based solar power has because of night, when obviously you're not getting any energy. And also, the beam will go through inclement weather, rainstorms and stuff, which will also tend to block the ground-based solar power. And as a consequence, since it's continuous, you avoid the problem of energy storage, which is quite expensive. Being an economist by training, I think the most important finding of the IAA report is, and I'm quoting here, economically viable solar power satellites appear achievable during the next 1 to 3 decades. This is quite an improvement over some of the things which have been said in earlier studies. There has been a general consensus in, I believe, every significant study, both here and abroad, that space solar power is technically feasible in the sense that there's no showstoppers. But this is the first major study which has come out and said that it's a good chance it'll be economically viable. The community as a whole has generally for some time said that space solar power is technically achievable in the sense I just mentioned. And the real issue is, can you get the power at a cost which is competitive with other options? And partly, I think, because of John Menken's new approach to space solar power, which I think he will discuss in some detail, that now appears achievable. Now, let's look at some of the benefits of space solar power beyond the simple fact that it brings down energy. The sun produces 1 to 10 trillion times the amount of energy which is currently consumed by the human race. So if you bring just a small percentage of that down to Earth, that's potentially can solve all of your energy needs. The other thing about space solar power as compared to many other options is it's highly environmentally benign. If you take the base case that I'm talking about, the beam's not a problem. Naked humans can walk through, birds can fly through. That's not true with some of the other options, but with the base case one it is. And that's very nice from an environmental viewpoint. Also, it produces virtually zero carbon dioxide, and as a consequence is very green in that regard. And to the extent that carbon dioxide is a problem with regards to climate change, this would greatly mitigate that particular problem. There's also some additional benefits. We have talked in this country for many years, both parties, Republicans and Democrats, about a problem of energy independence. America spends about $700 billion per year on oil imports. That was just before the recession. Probably a little bit less now, but it'll get higher once the recession is over. And a lot of those oil imports come from countries which are unstable and are not necessarily friendly to the United States at all times. And so that's a serious national security problem. With space solar power, if it works out well, we can bring down a large amount of energy, and as a consequence, getting ourselves into a situation where we're actually a net energy exporter. The way that works is space solar power can beam power to any place in the world, and therefore you can export it to other countries. According to the IEA study, if this approach works out really well, you'll end up eventually with annual employment on the order of 5 million individuals might eventually be realized. And you know, that's a lot of jobs. And these are also, for the most part, high-tech jobs. I'm putting on my economics hat for a moment. If we actually did that, that would mean that space solar power to the 21st century would probably be more important than the railroads were to the 19th century in this country. And for that matter, the automobile industry was in the 20th century and could be a real driver for the economy. Also, if we have a future where there's heavy energy scarcity, which might come about if in a number of scenarios where we don't have space solar power, you can certainly envision conflicts between nations over scarce energy supplies, which is an issue which the Defense Department is increasingly concerned about. And if energy is relatively abundant, which is a possibility with space solar power, that possibility goes away. Now, the first 3 points here refer to America. That's assuming that America built the space solar power stations. If we have an international cooperation where several countries are involved, then these benefits would be available to all those nations. Now, one of the things that the National Space Society is involved in is the Kalam National Space Society Initiative. For those of you who may not know, Dr. Kalam is the former president of India, and he's also an aerospace engineer of great renown. He was the director for India's first satellite launcher. He was later the former scientific advisor for the Defense Ministry of India. Currently, he's chancellor of the Indian Institute of Space Science and Technology and has a nickname as the Missile Man in India. He's sort of like Wernher von Braun in this country, except he's in India. And also, unlike Wernher von Braun, he went on to become president. Now, our initiative, which we're working with him with, is aimed at getting a bilateral American-Indian space solar power program going. And our next step is NSS will soon be sending a delegation to talk to Dr. Kalam in India, as well as some of the leading officials in the Indian space program. Both Dr. Kalam and the National Space Society encourage other countries to get involved in this, but at the moment it's a bilateral program aimed at India and the United States. Now let me put up as my last slide here some of the a long-run implication of this program. Let's assume it works out really well. Now, according to Wang Shiji, who's a founder of the Chinese space program, and he made this quote last August at a conference on energy and the environment in China, where I was also at and gave a paper. And I quote, "The development of a solar power station in space will fundamentally change the way in which people exploit and obtain power. Whoever takes the lead in the development and utilization of clean and renewable energy in the space and aviation industry will be the world leader." And that's a point that I happen to agree with. And now we'll bring up the next speaker, who is John Mankins. And John, you might want to come up here and worry about your AV. John is the co-chair of the IAA study. The other co-chair is also here, and that's Nobu Kaya. Would you like to stand up? He is a professor in Japan and one of the leading researchers in Japan on space solar power. Currently, Japan is probably the leader in the world with regards to space solar power, spending considerably more money than we are. So we're very happy to have him here. As for John, he's also the Chief Operating Officer of Managed Energy Technologies. He's the President of the Space Power Association. He had a career at NASA that spread across 25 years. At NASA for a while, he was leading a program that spent $800 million per year in an R&D program. And while at NASA, he was also the go-to guy for all the studies on space solar power that happened during his tenure. Today, he's generally acclaimed to be the world's leading expert on space solar power. John?
Good morning. I have only one correction that I need to make to the introduction that Mark Hopkins so kindly made a few moments ago, and that is that I am no longer the Chief Operating Officer of Managed Energy Technologies. I'm a 25-year veteran of NASA, but these days I'm an entrepreneur, which means you start companies and you kill companies. So Managed Energy was a company that I started with a business partner in New York, and after several years, it turned out that one was not going to thrive, and so we agreed to go ahead and terminate it. So please don't quote me as that, cite me as that, because that's not correct. So I apologize. So as you have heard, during the last several years, starting around 2008, the International Academy of Astronautics, which is an international honor society in the international space community, formed about 50 years ago, conducted a study of the topic of space solar power. Although there have been numerous studies conducted over the last 4 decades plus, since space solar power was invented by Dr. Peter Glaser of Arthur D. Little, there have been numerous national activities. There have been system studies. There's been technology development. There have been activities involving different agencies and different companies and different universities. But there has not been an international assessment of the topic generally, writ large. There was one focused activity looking at spectrum issues a few years ago, and it's cited in the Academy report. The goals of this study, which was implemented under the auspices of Commission 3. If you don't know the International Academy, I recommend you to their website, iaaweb.org. The Academy is organized into a series of technical commissions which cover different aspects of astronautics. One of these is space systems and technology development. So this study group was implemented under the auspices of that commission, which is Commission 3. And the goals were to determine what role space solar power might play in the future energy needs of Earth, to assess the technological readiness and risk of space solar power, and if appropriate, i.e. if it was our assessment that the risks are extraordinarily high and the readiness is extraordinarily low, then we wouldn't proceed. But if it was appropriate, then to frame a notional roadmap for the international community to consider in going forward into the development of space solar power. We also looked at a range of prospective synergies between space solar power systems and technologies and other applications, and we looked for opportunities to use extraterrestrial materials in future space solar power activities. And although it's not on here, it's a detail, but we also looked at a wide range of policy-related issues concerning space solar power. And all of these, I won't go into all of these, of course, this morning, but all of these are written up in the full report from the Academy study. One of the foundations of the work was to look out at the literature and determine what are the requirements for energy internationally over the coming century. So we went from 2010 to 2100, and we found that there are a wide variety of opinions, but that fundamentally the projection is that the populations will continue to grow unless something happens to radically reduce populations during the next 80 years. So by the end of the century, the high water mark in terms of projections is something like 12 or 13 billion individuals on the planet, and that energy consumption will continue to grow and grow radically. Whereas today, and I use kilowatt hours because I'm not good with barrels of oil equivalent, but so it's something like 120,000 billion kilowatt hours are used today, and that's all sources of energy, heat and transportation, everything else, and that by the end of the century it will quadruple as emerging countries like emerging powers like China and India continue to improve the standard of living for their people, as other regions like sub-Saharan Africa or the Oceania, the countries like Indonesia and so on continue to develop. There's going to be a need for more energy, not less. However, at the same time, there is a scientific consensus that there's a significant issue with regard to climate change, which is believed to be anthropogenic in origin, i.e. the accumulation of greenhouse gases in the atmosphere is causing or is driving changes in the Earth's climate. So if you imagine taking our existing suite of energy sources, predominantly fossil fuels, and you quadruple that by the end of the century, and you look at the accumulation of greenhouse gases, you get enormous numbers in terms of the degree of change in the Earth's atmosphere relative to the atmospheric constituents in the pre-industrial age, before 1850. So what the Academy did is we didn't reinvent any of this. We just looked at it and said, okay, what does it look like? And then we found that a lot of the work that's done in terms of climate change studies is a lot of scientific detail. It's very hard to get your hands around it and use it in some fashion because there's all these numbers and all these curves and all these projections. So what we did is we instead chose 4 scenarios. Not saying any one of these scenarios is the right answer, just saying these 4 scenarios approximately scope the future, the next 80 years. And these were 1, scenario alpha, business as usual works out. Turns out everything we're doing now is fine. There's no reason to be really concerned about greenhouse gas emissions. Turns out that climate change is going to be on the low end of everything and it's going to be fine. Turns out we don't really need a lot of new energy sources, but we need a lot of new energy. And the demand for energy will continue to increase, and so on. Scenario beta assumes things don't work out just fine. We continue on our current course, and climate change is on the high end, i.e. it's warmer than the moderate projections. Greenhouse gases accumulated more rapidly, and the frog gets cooked as a sort of a short title for this scenario, refers to the old story about how if you drop a frog into a pan of hot water, the frog will escape. But if you put a frog in a pan of cold water and you heat it slowly, you end up with frog soup. So in this case, we're the frogs, and we're in the pan of cold water getting heated slowly. Scenario gamma looks to the issues having to do with the Hubbert curve hypothesis, and that ultimately fossil fuels, which are a finite resource that's accessible within the Earth's crust, are depleted, and looks at different cases for depletion of things like petroleum or coal or natural gas. Again, this is looking out over the next century, and the big issue is not so much that we run out of oil, we probably will never run out of oil, but rather that oil production annually peaks while demand for petroleum energy and petroleum petrochemicals doesn't peak, and that leads to price increases. So that's scenario gamma, and scenario delta is, the last one is, we assume that there will be significant increases in green energy or green environmental policies, and that those work out, and that those are designed to mitigate the negative things in scenario beta and scenario gamma. So then taking these 4 scenarios just at a very superficial level, we made some statements about what might be the outcomes during the remainder of this next 100 years for the energy marketplace. And then we use those to evaluate space solar power options. Now, as Mark alluded to, there are a host of different systems approaches that one can envision, different architectures for space solar power. And it's not really possible in a finite amount of time for a group of volunteers, however well-meaning, to look at scores of options with any kind of rigor. So what we did was to narrow it in on 3 specific concepts. I don't think I have a laser pointer, but that's okay. The first one is a version of the 1979 reference system concept. That's the upper left. The next one is a modular laser concept. And the third one is a highly modular microwave concept that involves what's called the sandwich approach. And these are all described in greater detail in the Academy report. But the key point here being these 2 use lasers. Oh, thank you. Thank you very much. 2 would use, oh, it's green, I like that. 2 would use microwave, the updated reference system, and the sandwich structure. 1 would use laser. 2 are more modular, and 1 is less modular. All of them would be based in geostationary Earth orbit. All of them are baselined to deliver approximately 1 or 2 gigawatts, and all of them were evaluated in terms of their technologies and potential feasibility. And in a little while, I'll show you a short animated clip on these 3 concepts to get a little better idea about them. One of the things that we wanted to do, we didn't get in, I should say what we did not do. What we did not do is a rigorous end-to-end systems analysis study with systems modeling of any of these concepts. We were an unfunded study. The International Academy of Astronautics is an academic organization. It is not a programmatic organization. So we didn't develop any models or any spreadsheets or anything. Rather, that we did was high-level characterization and relied on existing literature, and then did evaluations based on specific criteria that we had identified. In the case of the technical criteria, in terms of these 3 types of solar power satellite concept, we looked at factors such as how much did we judge it would take to get to first power from a system, so cost of first power, what were the overall life cycle cost and economic prospects, the technology readiness and risk for each of the concepts. This was quite an elaborate assessment that was done. The anticipated ease of technology maturation, i.e. how hard is the technology maturation R&D program likely to be? Policy issues, what are the challenges with regard to key policies? Questions such as orbital debris mitigation or cause or origination. What about the potential weaponization of space solar power systems concepts, and so on. And what are the prospects for non-solar power satellite applications of space solar power systems and technologies? And the bottom line from this technical assessment was that the classic microwave concept, this is an update of the 1979 reference, is still quite poor. It's not a strong competitor for a number of reasons. The modular laser concept is better, but it has still some significant issues. One of those issues is that it's likely to continue to be more expensive, and therefore its economic prospects continue to be fairly poor. And it has some policy issues with regard to the risk or the possibility of harming retinas or weaponization and so on. And the modular RF sandwich concept, as I mentioned, it came out looking like the most attractive for a number of reasons. We also evaluated the 3 types of concepts against the 3 energy and environmental scenarios that I described. And what we found was that the modular laser and the modular RF concept were both quite similar, and the RF Classic was a little bit worse in terms of that. Probably the worst situation for the updated version of the reference concept is this much higher cost for upfront investment before you get to the first useful power. And if scenario alpha turns out to be true, i.e. business as usual, works out, then there's not really a driver for that kind of massive upfront investment. So the modular concepts have a big advantage there in that the upfront buy-in cost is significantly lower. And that was really enough to make the difference here. So in summary, the Academy finding is that the Type 3, this is the microwave sandwich concept, really looks the most attractive for the reasons cited. The Type 2, which is the laser concept, is not as attractive, and the update of the 1979 reference continues to be quite challenging technically and programmatically. A great deal of information on all of the details of this analysis approach and the findings are presented in the Academy report. Ultimately, it was the judgment of the Academy study that space solar power is technically feasible, and there is a very reasonable prospect that it can be economically viable, as Mark mentioned, within the next 1 to 3 decades. This is not the same thing as saying that it is economically viable, because there's still, although it's our judgment that a lot of the technologies that are needed are now in the laboratory. In fact, in the case of the modular system concepts, they're virtually all in the laboratory. However, there's still a lot of work to be done in terms of engineering, research and development, and technology demonstrations in order to validate the performance of these technologies in operational space solar power systems concepts. However, it was our finding that the time frame that would be necessary to get to a multi-megawatt space solar power systems demo that would probably be capable of delivering power to Earth in the range of $1 to $5 per kilowatt hour, which is high, but it's not astonishingly high, that this could probably be done in the next 10 to 15 years. Namely, that it's not a 40-year or a 50-year vision. It's not something for our grandchildren. Rather, you're in the room and you happen to have grandchildren. It might be something for your grandchildren if they're around already. But it's really something that could be accomplished by this generation of aerospace engineers and technologists and program managers. One of the most significant findings in the report, and again, because in the interest of time, I didn't include it in the front part of this ViewGraph package, but it'll be in the backup part, is that this initial demo could be done without the development of a new reusable launch system. This has always been one of the great barriers to large-scale commercial ventures in space, is that first you have to have really low-cost access to space before you can do the new venture. But in order to justify doing the venture, you have to be able to demonstrate that you can launch it. And so you end up with this inherent chicken and egg problem. Well, what we found was that because of the smaller scale, smaller scale is still large. This would be a platform for the pilot plant on the scale of the International Space Station. But because it's much smaller than the large solar power satellites, it in fact makes economic sense to do such demonstrations with existing or already on the books expendable launch vehicles. Things like a large-scale buy of Delta IV Heavies, or a large-scale buy of Falcon 9s or Falcon 9 Heavies, i.e. that these price points in the low thousands of dollars per kilogram to low Earth orbit are enough. They're low enough that you can do these demos successfully, you can plan them successfully, to get to the $2 or $3 per kilowatt hour price point. Although it wasn't highlighted earlier, I just mentioned that this prospective market niche in the $2 to $3 range really was an outcome of a study that was done in 2007 in the U.S. by the National Space. It was done for the National Space Security Office, unless I've reversed security in space. I did. Okay, National Security Space Office. I apologize. It's NSSO. At any event, this study really identified the idea that there's a niche for power in the range of a couple of to $3 a kilowatt hour in forward operating bases for the United States military or its allies, or for emergency situations, rescue, and so on. And it changed rather dramatically this opportunity to identify the pilot plant as a potentially commercially viable option. The only other thing I'll highlight from the report, which is embedded in this more abstract diagram, is the fact that there is, however, though there's not a need for a new reusable launcher in order to proceed with space solar power, there absolutely is a need for new in-space operational capabilities. Things like low-cost LEO to GEO transportation systems, things like in-space assembly and robotics and others. So those are absolutely enabling, even for the pilot plant, but it was our judgment that there's no real fundamental barrier to any of those having their first-generation systems available in time to support a pilot plant in the 10-year time frame. So I just would like to highlight very quickly a couple of the key findings and recommendations. So a fundamental finding, which is not news but is notable, is of course that fundamentally new energy technologies appear to be necessary. It doesn't appear that we can go from 120,000 billion kilowatt hours per year of consumption to 480,000 billion kilowatt hours by the end of the century, while at the same time reducing overall greenhouse gas emissions using the set of energy technologies that we now have at hand. Solar power satellites appear to be technically feasible as soon as the next 10 or 15 years. And economically viable solar power satellites appear achievable, but more information is needed concerning both the details of potential system costs and the details of the markets to be served. And I'll skip the next two because they have to do also with recommendations, but I'll just mention that we do believe that low-cost Earth-to-orbit transportation is absolutely enabling for full-scale commercial systems. No change. That's been true since space solar power systems were first looked at. It's only the change in how you get there, this new idea that you can do a large-scale, intermediate-scale pilot plant without these that looks very interesting. The Academy strongly recommends the need for both system studies and technology development programs, flight experiments, and ground R&D. And probably the solar power satellite concept is sufficiently different that it will demand some kind of large-scale demonstration like the pilot plant before it would ever be accepted. There are enough uncertainties and there's enough difference in opinions about different technical approaches and the architectural issues and the component technology issues that nobody's ever going to make a large-scale investment in a development program for the full-scale system unless there are these stepping stones first, unless there are proof of concept technology experiments and studies, initial technology demonstrations, a subscale but still large pilot plant demo. This is analogous to the strategy that was followed in NASA with regard to Pathfinder Sojourner. So nobody was going to buy the Mars Science Lab unless 20 years ago there was initially this full subscale but end-to-end system demo called Pathfinder Sojourner in the early 90s. Nobody was going to buy the use of electric propulsion for deep space missions without the full-scale demo of Deep Space One, and so on. So there are times when you have this sort of transformational system concept, it's not going to get large-scale funding until you have a real demonstration. And that's one of the findings of the Academy. And lastly, that there are a number of policy and regulatory issues that have to be explored concurrently with space solar power and wireless power transmission system developments. So in terms of the recommendations, each of these 5 bullets has a number of sub-bullets. I refer you to the actual Academy report for those. But just to highlight, so it's the recommendation of the Academy that government and commercially funded space solar power systems analysis studies need to be undertaken in order to fully resolve the research and development goals and objectives that have to be achieved. This is just to highlight a rather detailed point, but an important one, that since each space solar power system concept is a little different, each one has different technical requirements that you have to prove in the technology development program in order to know whether or not that space solar power system is going to be viable and at what price point. Future economic analyses have to look at the potential role of non-space related government and international funding. For example, from organizations in the U.S. like the Department of Energy, or from energy companies, not just from aerospace companies. Government and commercial organizations should consider undertaking space solar power and related technology R&D And if you look across the technologies that are involved, and again, I'm referring back to the quotation that Mark Hopkins offered earlier from the statesman or the elder scientist in China, what you end up finding is needed for space solar power are all of the critical technologies that you need to do anything ambitious in space. Low-cost access to space, affordable and efficient and reliable transportation from one Earth orbit to another and basically throughout the inner solar system. High power at low cost throughout the inner solar system. Assembly of large and complex systems that are largely autonomous in their operation, don't require thousands of people in sustaining engineering and mission control on the ground, and so on and so on. So you end up with this suite of capabilities for space, which if you develop them for space solar power, even if you never build a fully economically viable solar power satellite, you have fundamentally changed how space is done for the remainder of the century. That the necessary policy and regulatory steps to enable space solar power and related R&D need to be conducted, leading to systems-level demonstrations, and that international organizations can play a very constructive role, including the International Academy, in fostering and guiding future space solar power studies. A particular idea which is in the report itself, which is not highlighted as a recommendation, but which I would refer you to, is the suggestion that maybe the right way to get started with the international development of space solar power is through the formation of an international science working group, like the Mars Exploration Program Advocacy Group, like the International Lunar Exploration Working Group, like the working groups for the small body science or for human exploration. That it's premature to really form a company, an international consortium for space solar power. It's probably premature to talk to anybody about doing something like a space station type program where you've got an international treaty organization. All of that might be down the road, or maybe there are other programmatic paths. But one thing that could be done in the near future is to form, involving the right agencies, the right companies, the right universities, to form an international working group to start coordinating and discussing on a more regular basis space solar power and related research and development. And that from this, one could readily see bilateral programs like Cassini-Huygens, the mission to Saturn several years ago, which is still in orbit around Saturn, was a collaboration between NASA and the European Space Agency. But one could easily see coming from this kind of process of coordination and this creation of an international working group, such future collaborations. And with that, I will simply show you, these are all in the backup slides, so you have to wait, get a copy of the disk. I'll just show you, these are the principal team members for the study group. There were also a number of individuals who participated in a major workshop for the study, which was in September of 2009 up in Toronto, Canada, which was sponsored by Space Canada. And there's a very a comprehensive listing of the individuals who contributed to the study in the appendices of the book itself. So this is this video clip just shows some clips. So this is, of course, the animated version of the logo for Space Canada, which very kindly sponsored the development of this video. Anyway, so this is concept one. This is the 1979 reference system. You see in this concept a large transmitter, a thermal management system at its base, and then connected to it a set of independent large solar arrays, and it delivers power to the Earth in that fashion. Concept two in this listing is also a microwave concept. This is the updated version of the sandwich. You see some large arrays of mirrors. These are thin-filled mirror structures, basically solar sails that have been captured, and they're reflecting sunlight onto a secondary mirror, and from there onto the microwave transmitter. And thence to Earth. And then concept three in this listing is the laser concept. So independent modular satellites with the solar arrays, the laser projector, and its own thermal, and then that's repeated multiple times. Again, delivering power to the Earth. And then concept four, which was another major finding of the Academy report, is the idea that with these modular architectures in particular, that one can envision taking a number of the same pieces, these solar sails, pieces of the transmitter, a small-scale version of these, the secondary reflectors, and make pretty readily a pilot plant demonstration, which is directly on the path to one of the larger-scale implementations. And with that, thank you very much.
On behalf of all of us at Space Canada, I would like to congratulate my friend John Mankins and the International Academy of Astronautics on this historic accomplishment. I would also like to thank my friend Mark Hopkins and the National Space Society for the invitation to have us here today as co-sponsor. The old joke when one is explaining something complicated is to say it isn't rocket science. Well, this is rocket science, but thanks to John Mankins, the basic facts giving rise to the need for the research are quite easy for us all to comprehend, and I especially appreciate his roadmap approach. Essentially, we're here today because based on a chance meeting in Scotland in 2008, an invitation worked together led to the International Symposium and Workshop, which took place in Toronto in September of 2009. We had an interdisciplinary approach taken at that meeting, and we were also treated to an exposition of Dr. Kaya's latest research with the students, which was quite amazing. From our view, space-based solar power research and development is of paramount importance given the rapidly developing challenges facing our Earth. Atmospheric carbon dioxide and its effect on climate change, as well as the basic human need for secure, safe, renewable energy, must be resolved if we are to survive and to continue our standard of living. We at Space Canada are dedicated to the proposition that this technology bears out the test of further development and implementation following the success of that development. And I'll be quick about this. There are pessimists in the world today who feel that the inventive spirit has lost its way, that we cannot solve the very problems that in some way we have created for ourselves. While it is true that many of our difficulties can be linked to the presence or absence of various forms of technology, it is equally true that human inventiveness, creativity, and common sense can solve a problem just as fast, if not faster, than it can create one. The amazing life of the late Mr. Jobs is testament to that for us all. This optimism is my own fundamental belief and the reason that Space Canada's support of this all-important work. As well, activism in support of the great human experience of space must be supported and promoted. The National Space Society is yet another example of the ongoing greatness of the American spirit. Our own Canadian Space Society, while smaller and a chapter member of the NSS, is a vibrant and affirmative force for space development and exploration, and we strongly urge young Canadians and Americans, as well as young people all over the world, to get involved and to help move our societies forward. And my final comment is to prospective investors out there. Financial opportunity always starts with a dream, then a prototype, then finally a common human need. Space-based solar power might just be exactly that. Thank you.
We'll take some questions for me or John or George.
So in particular, the last time that there was a real look, and this was a more rigorous look, was at space solar power was in the 1970s. Or 1990s rather, during NASA's Fresh Look study and the successive programs which I led. And one of the things that was, which we could not see a clear way around at that time, to avoiding a very large and lengthy government program to mature space solar power, was the need as you scaled up in power from a 100 kilowatt experiment to a 1 megawatt experiment to a 10 megawatt demo, the need to fundamentally re-architecture the spacecraft system. So the power management and thermal management and guidance and control and so on. And so in looking at that, and you can find a lot of details on this approach to a roadmap in the National Academy of Sciences, National Research Council review of NASA's roadmap for space solar power from 2000-2001. So one of the things which appears very promising now is this idea that through these hyper-modular architectures that you can build fairly tractably, i.e. with tens of millions of dollars, a prototype of a module. And for a bit more money, you can make a bunch of copies of those modules. And that if you do follow one of these modular architectures, and this is still one of the problems for the updated version of the reference system, these modular architectures, you don't end up having to re-engineer the whole thing just because you're adding more modules if you get your interfaces right and you get your the fundamental device choices right. You can upgrade devices. You can go from an initial 70% efficient amplifier to a 75% efficient amplifier without re-engineering the whole electronics food chain. You can go from aluminum spacecraft structures to carbon composite spacecraft structures. This is like the evolution of the internet over the last 20 years. Nobody had to go back and fundamentally re-engineer TCP/IP with every new generation of laptop, although it's possible Microsoft would have liked that. It didn't end up, I don't mean to be bad to Microsoft, just as an example. So the way that the interfaces are handled and the way that the World Wide Web has evolved, all sorts of devices come and go, but the network is basically the same. These networked approaches really suggest that a breakthrough is possible in terms of the schedule, and if the system architectural approach is sufficiently modular in terms of the cost. There's no radically new, it's not carbon nanotubes, it's not, we suddenly have infinitely high temperature devices. Rather, it's just, if we can get to the point where we can come up with a way to make a 10,000 ton spacecraft out of 100 kilogram modules, tens of thousands of 100 kilogram modules, we win. Because it becomes like making laptops. That's the fundamental change in the last decade.
We got another question? Yes? Let me repeat the question. Basically, how do you come up with the conclusion that it may be economically viable in 1 to 3 decades, given various assumptions?
Right. So in the mid-1990s, when we did the Fresh Look study, the price of a barrel of oil on the international market was about $16 in today's dollars, $16 or $17, and now it's $100. Our fundamental assumption in constructing our scenarios was basically that it's never going down by a factor of 5, and that there's going to be some levelization because of demand for energy and related to the demand for carbon neutral energy, or at least carbon minimal energy, that the price of energy is going to stay at a high level the way it is now or even higher. So that was our fundamental assumption in terms of the markets. And that wasn't something we made up. It was just based on looking at the projections from the International Energy Information Agency, from the International Energy Agency. It just nobody believes that the price of energy is going to drop fundamentally. And nobody at the moment is saying that there's not going to continue to be a strong demand and strong policy incentives, even without increasing those, for green energy. So given those assumptions that there will continue to be incentives for green energy, and that the conventional energy will not suddenly plummet in price, then that's how we get to this projection that if we can get the right numbers for the systems, we'll get the profitability, we'll get the market viability.
The question is, what are some of the most important incentives for green energy?
Yeah, so there's been for a long time for space an incentive which was advocated, I think, first by Congressman Dana Rohrabacher, which was a very nicely phrased incentive, which was zero G, zero taxes. I think Dana was an early advocate for that. The problem with that incentive system is first you have to have profits before you can pay taxes. And so you've got to have something to help you get over the barrier to profitability. And the way that it works with solar or wind is that you have a combination of ways in which governments, through policy objectives, can support the development of new energy, which, if we followed those tracks, this would be fine. One is enabling research and development at an appropriate level. The solar energy technology program in DOE is like $100 million a year annually. Another one is specific focused incentives like tax breaks and so on for specific developments. And the third is feed-in tariffs. So for the initial few years of a new energy technology, you feed it in as a part of the overall energy mix, and ratepayers, because it's green, pay more for policy reasons. So those three, I think, are a really powerful combination. It's the only reason why now gigawatts of solar are being produced globally. It's the only reason why there are hundreds of millions of megawatts of wind being deployed annually. It's for those three. And so I think not to say that zero-G, zero taxes isn't an interesting idea, and it was a really good way to articulate it, but those three incentives have worked, and I think they're the right ones.
The question was, how much would the pilot plant, roughly speaking, cost, and what are the key technologies on the road to pilot plant development?
Okay, so not from the Academy study per se. So in terms of, I'm going to give you an answer, but I'm going to give you an answer that's my opinion, not the consensus view of the Academy. So the Academy didn't get into cost estimates, didn't do end-to-end system studies, and so on. So a number that was developed to do this for the NSSO study in 2007 that I referred to earlier was based kind of on a challenge which the then director of the NSSO, Joe Rouge, gave to me. I was the lead for the science and technology team for the NSSO study. And the challenge was to do something tenable in about 10 years for about $10 billion and about 10 megawatts. So the 10, 10, 10. And that really got me, and that was partially his challenge and partially my feedback to his challenge. And that really informed our discussions within the Academy for this notion. So notionally, but again, not with a specific cost estimate, the idea would be $10 billion or less, 10 years, and deliver on the order of 10 megawatts. So not hundreds of kilowatts and not hundreds of megawatts, but like 10 in 10 years in $10 billion. And we actually feel that that's actually quite a tenable challenge. A reasonable target. In fact, depending on your success and the system architecture, if you can get the right kinds of device efficiencies early and so on, maybe even a little faster and maybe even a little less money, but not wildly more money or not wildly longer. The specific technologies depend on the system concept. In the case of the system that I actually rather prefer, which is the one that the Academy found to be the most promising, is this very highly modular microwave-based technology. The single biggest tall pole to an initial system is thermal. It's what do you do about waste heat? Electronic devices are not perfect. They give off heat. If you've got a very highly, think about the fan that runs in your computer. If it's a little too warm, it runs, but there's no fans in space. There's no air. You can't use convective cooling. So getting rid of the waste heat or developing device technologies which can operate at higher temperatures without drastically losing efficiency. So for that one, that's the tall pole. For the others, there are other tall poles, and they're talked about in the report. Yeah?
The question is, John's been advocating a modular structure for some time, and it appears that one of the major conclusions of the IAA study was that this was a particularly good idea. John?
Yeah, I would say it a little differently. I'd say the modular approach that I and Professor Kaya have been advocating for many years, or for a number of years. He advocated it before I did. I had to satisfy myself that it was technically viable. That in fact is one of the findings. But I would say a little differently. I would say the other thing which is significant is that it was a very broadly based group. Not just Professor Kaya and I having a chat over a beer or after dinner or something, and that we came to a consensus that this was not a 30-year or 40-year problem. That in fact, and you look at many of the roadmaps that are out floating around now, they don't get to anything significant for 20 or 30 or 40 years from now. The idea that you could actually do this pilot plant with existing or near-term launchers, and that you could do it on the order of a decade. That's new. That was not something that we had talked about previously. Although it was, like I said, it was a challenge coming from the NSSO study. The idea of how would you actually do it was new.
Basically, the question here is what happens if there's a solar flare? Would this disrupt the system by maybe putting out a lot more energy than would otherwise be the case?
Yeah. So it's the two aspects of obviously from the energy that the sun emits. One is the photons, and those are virtually constant over very long periods of time. Not precisely constant, but approximately constant. So we don't worry about those per se. And then there's the particulates. There's the solar flares. There's these enormous solar eruptions, and they put out an enormous cloud moving at high speed of ions, and they cause a great deal of disruption. They cause the aurora borealis. Again, it's kind of system dependent, one of the other issues, this wasn't a topic that the Academy report looked at in detail. It's just another topic to be looked at in future studies. In the case of the reference system, where you have these enormous electrically active solar wings, like the space station solar arrays, but stupendously large, they're really vulnerable to solar particulates, to these high energy ions, because you have this enormous square kilometers of active solar array. So somehow protecting those is really hard. So that's a vulnerability for that system concept. For some of the others, like the modular laser or the hypermodular RF, the system elements are a little smaller, and they're, in the case of the laser, and they're a little bit easier to protect, but they still have an issue. In the case of the very modular concepts, those big wings that are in the illustration, those are thin film mirrors. They're just aluminum foil. You don't have to worry about them in particular, although you have to keep them from getting charged up or having differences in charge. But the main guts of it, the electronics, are all down in that one panel, and it's a lot more tractable to envision techniques to keep those protected, to keep them insulated from wild swings and voltages and so on, because they're being affected. You may lose service, but you don't lose the satellite. So I think this was certainly a great topic for future study, and I think it's going to directly depend on the system concept.
Let me answer that one. Yes, it could be a target. On the other hand, if there's a lot of satellites in space now which are of military importance, probably more important than a solar power satellite, which could also be targets. And if you were an aggressive nation, you'd probably hit those first. But if you got dependent on it, then you would have to make a serious defense. And for that matter, you have to seriously defend nuclear power plants on the ground. And it could get simply to the point that if you make a major attack against those, then that's war. And that's fundamentally how you defend it. All right, the question is, can you, I'll give this to John, can you cite some reports the IAEA has done in the past which have pushed national decision-making on something as important, loosely speaking, as space solar power?
So the proximate answer is no. The reason is kind of the way that the Academy chooses the topics that it will study in some depth. It tries not to mix in with current programs. So the Academy doesn't do studies on, like in the 1980s, what should be the reconfigured space station, the configuration evaluation process for the space station that led to getting rid of the dual keel. The Academy doesn't do stuff like that, because it's comprised of members from all of these different organizations, and it doesn't try to meddle in their proximate knitting. So one of the ground rules is it should be something which is further off and more strategic. So, for example, a study that came out several years ago had to do with the threat of impactors, of objects, asteroids and comets and so on, and what to do about that. And it's hard to trace exactly what influence the Academy study had versus others, but now you see an increasing discussion on planetary defense as one of the big issues. And it certainly didn't do any harm to have this international group talking about it and promoting that as a topic. Another one, obviously there's past studies on orbital debris and the need for international action, and a range of others. But I'd say in general, the idea which came out of the study, which is that it's not 35 or 40 years off, it's maybe as close as 10 years, that was a sufficiently new result that, it would cause, if it's to be acted on, it would cause a more significant change than most.
The question is Secretary Chu, who's head of the Energy Department's prediction that we can get ground-based solar power down to 5 cents per kilowatt hour occurs, what would be the response with regards to space solar power program in general, and in particular, what would this mean for how far we'd have to push launch costs down?
Yeah, so it's a good generalized number, and the levelized cost of electricity. So I'm not going to comment in particular on anything that the Secretary of Energy has said. But in general, the levelized cost of electricity is an excellent figure of merit to use, and it's the one that we pursued in shooting for, as a long-term goal, 10 cents a kilowatt hour. The thing we've observed from energy markets, and again, one of our basic assumptions is energy is not going to become radically cheaper. One of our operating assumptions, one of our observations is 10 cents a kilowatt hour would be more than adequate with costs of space transportation on the order of $500 or $1,000 per kilogram to low Earth orbit. I.e., it doesn't have to be $50 a kilowatt hour. It's much lower than Falcon 9 Heavy and so on, but it's not impossibly lower. But the significant issue in looking at these things is sort of look at apples to apples. So you might get to 5 cents or 7 cents or 4 cents a kilowatt hour for solar when the sun is shining brightly. The question is, can you deliver that 24/7? How are you providing baseload power? And so one of the trade studies that's been done by others, it's not done in this study, but it's alluded to in the appendices in the Academy study is what do the numbers kind of look like? What's the power delivered from wind and solar systems kind of look like over time? And what are the other issues that might be redressed by a mixture of ground solar, ground wind, hydro, and systems that were 24/7 like space-based solar power? We're not advocating, in fact, nobody in any of our meetings has ever even suggested that space-based solar power becomes the solution. It's a rather nice solution because if you have one plant in orbit above, off the coast of South America, one satellite could deliver power to pretty much any place in North America or South America. And it could provide that with fairly rapidly changing. Like tomorrow's going to be completely overcast in the Northeast. Power can be delivered to the solar energy collectors in eastern Canada to provide power to the Northeast. The day after tomorrow, it's going to be bright and sunny in the Northeast. We can deliver that energy rather to a chemical processing plant in South America and use it to drive the production of biofuels, all from the same plant. So you don't have that kind of flexibility with any other conventional terrestrial renewable energy option.
You should show that slide.
Let me add to that. If a lot of the technology which you would have to push in order to get ground-based solar to be very cheap, particularly in the case of solar cells, would also tend to drive down the cost of solar cells in space. In fact, that's been tracking in the last, particularly in the last decade or so, quite well. Another factor is you can send this power anywhere, so you may be able to get ground-based solar in Arizona down to the cost you're talking about, but probably not in Seattle. And we could beam the power to Seattle.
So if you could turn up the cardboard flap on the projector, thank you so much. And if you would step
Okay.
So just as an illustration, with the kind of electronic beam steering system that Professor Kai is developing at Kobe University, you could, in principle, from a single solar power satellite, this is the X here, you could deliver power pretty much anywhere in North or South America. Not simultaneously, but flexibly, i.e. today you could be delivering it to eastern Canada for the whole northeastern seaboard. Tomorrow you could be delivering it to South America, etc. Similarly, a single satellite placed between Saudi Arabia and India over the Indian Ocean could provide power as far north as Moscow or as far south as South Africa, as far east as Germany or West Africa, and as far as far west as West Africa or Germany, and as far east as Indonesia. So if you can do that, and you can do it, as I said, on the order of 10 cents a kilowatt hour, you're going to make a lot of money. So but it's not displacing solar, ground solar. Ground solar is going to proliferate, we hope. It just provides you with a great deal of robustness that doesn't necessitate huge investments in ground-based energy storage everywhere. So the answer in general is no for a given solar power satellite. Now, if you wanted to build a different system that was based on different technologies and different wavelengths and so on, sure. But this is just like you can weaponize jet aircraft. It doesn't mean you don't have commercial jet aircraft that are extremely useful for global society, but you can certainly also build jet aircraft that are military. But it's not the same aircraft except in acts of terrorism. So in this case, you can build a solar power satellite which in and of itself delivers energy at energy densities which are so high they get above Fahrenheit 451 with objects on the ground that are being illuminated. Our basic conclusion is nobody's ever going to do that. We don't advocate it. We don't think that it should be done, period. But if you build systems that are inherently, by the choice of spectrum and by the optics of the device, they cannot concentrate to a high enough energy intensity to burn anything, then it becomes extraordinarily difficult to ever weaponize such a system. And we think that's the only path that is sensible.
The question is, if you have to build a large number of rectennas in order to have your power being beamable to lots of different places, is that a major cost problem?
Yeah. So, and I might mention that these ellipses are just to indicate the shape of the ellipse. They're not to scale. So, I mean, this is just because as you go away from the directly nadir point, you get cosine. And so, but they're tiny by comparison. So, this is one of the fundamental issues that has to be resolved through R&D is how much is it going to cost per square meter for the rectennas? Inherently, with the microwave case, the receiving antenna is like the Arecibo dish. If you've ever seen photographs of that, it's a microwave dish. It hangs over this intersection of several mountain ridges, and underneath of it is farmland. So about 80% of the sunlight comes through the Arecibo dish. It's a perfectly nice mirror for microwaves. Similarly, for the receiving antennas for space solar power using microwave, we anticipate these things would be elevated, and they would not interfere with the use of the ground underneath for things like farming or wildlife preserves or what have you. Analogous, if you've ever driven underneath the power lines, which are actually much higher energy density, and they just sort of go marching across the landscape, these things the mesh would sit up there like a roof. In terms of the economics, this is one of the issues in the report that's highlighted. If the cost per square meter, the cost per kilowatt hour delivered for the rectenna is high, then you end up not being able to do this kind of strategy. But the goal would be, how do you make it cheap? The last time it was looked at with any rigor in terms of manufacturing studies and so on, it's actually back in the 1970s. People don't tend to focus on this issue. So there needs to be research and development to do two things. One, to improve the efficiency, the energy conversion efficiency of the receivers, and two, to establish the manufacturing cost point for them. But I have to say the device technology is astonishingly simple. If you go to the Radio Shack and you buy, again, not endorsing Radio Shack, if you go to the electronics shop and you buy a diode and an LED and you connect the two and you hold it near your microwave oven, if it's an older microwave oven and it's a little leaky, the wire on the diode will light up the LED, and you've just manufactured your own rectenna. That's it. So there's a lot of details in terms of the design and know-how in terms of connecting them and all that, but the actual physicality, the physical pieces that go into these receivers is a bit of conducting metal and a couple of diodes and some wire. And so it should be amenable to extremely low-cost manufacturing, but it's to be proven what's the price point.
Yeah, let me add to that. One of the major environmental advantages of space solar power as compared to ground-based solar is that if you put solar cells on the ground, you basically kill anything under it because no sunlight gets there. And you have to cover a much larger area with solar cells than you would with one of these receivers. And the sunlight will, as he pointed out, most of it will go through the chicken wire sort of arrangement, which is your receiver. And so you can continue to have life and agriculture, et cetera, under the receiver, which you probably, for the most part, cannot do with ground-based solar. The question is, for John, what are the top 3 to 5 applications that you see with regards to relatively near-term profitability using what we're talking about here?
So to first order, there's space solar power, and then there's associated systems and technologies and so on. So I'm going to take into account the gambit. So to first order, if you went in and you built the pilot plant and you established 1 or 2 companies manufacturing 40 or 50 expendable launchers at very low cost per year, you're going to fundamentally affect the rest of the launch industry. Because you're going to go from manufacturing, on average, there's so many launches in the world that on average a given launcher in a given country launches about once or twice a year. There's no way to ever get really low-cost launch as long as even expendable vehicles are only going to be used, and their entire production line and sustaining engineering is only going to be used once or twice a year. So one, you'd provide an incentive for that market. Two, so that's one. Two, in the longer term, this is long and short, you drive the development of low-cost launchers, reusable launchers, and that fundamentally changes the game for space, which has been explored in detail in the 90s by Langley Research Center with the Commercial Space Transportation Study, the CSTS. Very nice report, still germane today. In space, if you drive the development of low-cost in-space transportation, my own feeling is it's probably solar electric propulsion based. You fundamentally change everything you do. You fundamentally change what you're doing in GEO, because you now no longer have a huge restriction on what you can launch in geotransfer orbits. Every satellite in geostationary Earth orbit or near Earth space changes. You fundamentally change everything you can do for the moon, because if you can put 500 tons in GEO, you can put 400 tons around Mars for a really low cost, and so on. So the in-space assembly, if you develop the technology and the systems architectures to build 400-ton objects and larger, largely autonomously. I don't know if you noticed, I'm wearing a tie, which is a honeycomb and bees. And so this is the class of technology that's necessary. So this is a hyper-modular approach. It doesn't require a lot of intelligence. It doesn't require any managers at capital cities elsewhere. The bees take care of it. They're hard-coded, and they interact with one another, and they accomplish remarkably complex and affordable structures over the last millions of years. So with this class of technology, you can do all these things. And then, of course, for the space solar power systems themselves, if you have the capability to build at extraordinarily low cost, which you'll gain as you march down this path, to build very large aperture RF systems, there are never built any more satellites the way they're built today. You never build another satellite like a Swiss watch. Instead, you have architectures and you buy a cluster of machines and you assemble them to do whatever mission is that you want to do. So it fundamentally changes launch, it fundamentally changes operations throughout the inner solar system, it fundamentally changes how we do satellites, if this architecture proves out.
Let me add to that, longer run, as was pointed out in the report, if this program is successful, you'll create a market in space for the use of material resources in space for the construction of some components of the space solar power satellites. The advantage is that if you take material off the moon, it's much easier than taking it off the Earth because it's a low gravity well. And once you go down that road, you're beginning to seriously tap into not only the energy but the material resources of the solar system and really open the space frontier dramatically compared to what it is now. For John to comment on the job implications, particularly for the pilot plan, and perhaps you could also go on to what it means if the entire system in a big way is eventually implemented.
So this was one of the questions that came up in the discussions surrounding the peer review process. Was not an initial topic that we treated, but we didn't fold it into the report. Essentially, the pieces of solar power satellites are satellites. They're small satellites, and so if you think about the skill set that's necessary to build a system like ORBCOMM or GPS. It's that same kind of skill set, but a lot of them. And so I can't give you a number of how many jobs would be involved in doing the pilot plant. I don't have that readily at hand. It's easily calculable. But in terms of what we looked at, it was kind of a mix. So we looked at notionally how many people would be involved in the development of the satellite and how many would be involved in manufacturing and so on. It's almost all in manufacturing and operations of things like launch. It's a technical requirement that the systems have to be doable, and this is a question of economic viability, why we think it's likely to be achievable but not proven. You have to be able to operate solar power satellites like ORBCOMM operates its little constellation. You got to have, like on the weekends, 2 guys keep track of the constellation. So it's not a marching army. You can't afford to have a large number of labor hours per kilogram of solar power satellite. These things have to be, like bees, insect class intelligence, and largely autonomous, except by exception. And so almost all of the jobs that were projected, it was actually in Mark's slide, but it's in the report, at full scale by mid-century, this is full scale by mid-century, space solar power is like the automotive industry, meaning you have a very large and high-tech automotive industry of the past. You have a very large and high-tech workforce and a set of infrastructure with factories building pieces of solar power satellites. And a reasonable number worked out to be for something like 1 or 2. I don't remember the specific number in the report at the moment. It's a reasonable number. It's like a 100 or 200 gigawatts. So not a huge, not like all the power or something. And it works out to millions of jobs, all involved in making these things and launching them and making spare parts.
The question is there anybody in Congress that knows what space solar power is and is supportive? And the short answer is yes, but not enough of them.
A gentleman who was a very strong supporter when he was the chair of the House Subcommittee for Space and Aeronautics was Dana Rohrabacher. Another person who was very supportive was Gabriella Giffords before the tragedy where she was shot. So there have been a number of people who are quite knowledgeable and have been very supportive. And for one reason or another at the moment, none of them are chairs of committees. But hopefully that will change.
There's 3 questions here. The first one is what percentage of the energy market, or perhaps electricity market, are we talking about taking with space solar power? And the second one is let's compare this with fusion, given the amount of money we're investing in fusion, which is about $300 to $400 million a year. It's been going on for a long time. So assuming that's worthwhile, what does this imply for space solar power? And the last question is what should be the sort of minimal response with regards to the results of the IAEA report. So why don't you take the first one?
Okay. So the answer is a lot bigger. So compared to the existing satellite industry, which is on the order of 30 satellites a year, the scope and scale, even though the cost would have to be radically lower per unit, obviously the marketplace for space solar power and related systems would be stupendously larger. And the kind of numbers that we've looked at is, again, this is not trying to provide all of the world's energy from space solar power systems, but having a profitable and useful contribution. It may be 5 or 10% of the total energy consumption. So it's not again, we're not going after wind, we're not going after ground solar, hydro, or any of those things. It's just a question of, is space solar power potentially economically viable, and can it be really useful? We think the answer is yes. In terms of the second question.
Oh, that's the second question. Yeah, the second question was compared to fusion, what does this mean?
Yeah.
I think it's irrational to spend $300 or $400 million a year on fusion and nothing on space solar power. Both are aimed at, if they work out, a large percentage of the baseload energy market. Space solar power is much closer in a technical sense to being realized than fusion, which last time I checked hasn't even gotten to the point where you can produce more energy in a fusion reaction than it costs in terms of energy to contain the fusion reaction. So I think that a logical and rational approach would be to bring the space solar power research up over time to at least where it is with regards to fusion. In the near term, and John may add to this as well, I think the reaction to this study would be a program of, say, $10 million a year, which is roughly similar to what they're spending in Japan. What are they spending per year in Japan right now?
Yeah. So basically, the recovery from the disaster at Fukushima Daiichi is dominating the discussion of finance in Tokyo. So, but the need for new energy, alternative energy, is certainly providing a good chance. But we'll see a little better in April. The Japanese budget is an April 1 to April 1 cycle, not an October 1 to October 1.
Okay, Paul mentioned that if you capture 10%, of the world's energy market, of the current world's energy market. And of course, the world's energy market is going up over time. And you charge 10 cents per kilowatt hour for the electricity, then you would make a revenue stream of about $200 billion a year.
Okay, so it's a different talk, but I actually do do that shtick. The quick around the world tour is historically. I'll start in Russia. Historically, Russia's interest has been in the reflector concepts. So they're going to put large mirrors in space and try reflecting sunlight down to the Earth. Fundamentally, and for reasons that are easily explained on a chalkboard, this is a really poor idea, because you end up requiring, because the sun is a finite object, you end up requiring an extraordinarily large mirror that has to be perfectly flat across hundreds of miles in order to reflect a significant amount of sunlight down on the Earth. So it's an interesting idea. It's a nice way to test solar sails. It's not very useful. More recently, there's actually been a couple of workshops related to space solar power and advanced energy technologies that are being done by a group in Russia and by the University of Houston, Alex Ignatieff. So there's a little bit of movement there, but there's certainly no program. In Europe, there's been a number of activities. I'm working east to west, I guess. Europe, there's been a number of activities, probably some excellent centers of expertise. The universities in Italy, universities in the UK, a lot of relevant technologies, and obviously robotics and small sats. Programmatically, the centers of activity have been at the European Space Agency and within EADS Astrium, where there's a significant corporate interest in doing something that is both space-related and related to space solar power, i.e. for sustainable energy. Moving further west, obviously in the US, there's activity, there's in fact a new program, which is minty fresh, just started in September, under NASA's revived NASA Innovative Advanced Concepts program. This is the first NASA-funded space solar power specific project since the early 2000s, approximately a decade. And that's for a new SPS concept. As it happens, I'm the principal investigator, and Professor Kaya is one of the two co-investigators, so it's an international project. Obviously in Canada, Space Canada and the Canadian Space Society continue to be active supporters, as obviously the National Space Society is, and there have been some activities looking at alternative applications in Canada for some of the key technologies. There's no programmatic activity, though, within the Canadian Space Agency, which is a shame, because historically they had some very nice technology developments. But the CSA is kind of in a state of uncertainty about the Canadian Space Agency in terms of its future direction and goals. A stupendously fine announcement was the one from the McDonnell Detweiler and Associates, MDA, and Intelsat about demonstrating and going commercial with geostationary Earth orbit-based servicing and repair of satellites, which is, they took it as a given that you can just go do this. Now, they've got some problems in terms of where they get future funding and whether or not they're going to get cut out of U.S. competitions and so on. That was just announced last week. But the fundamental judgment of those two organizations is the idea of doing servicing and repair automated with robotics, well, we'll just build it and do it commercially. So it's a very nice demonstration that B-class intelligence is a tractable solution. In Japan, obviously, there's a substantial body of expertise in universities. There's an ongoing government program. There's an ongoing goal in the Japanese space law, fundamental space law. There are 9 goals. One of the 9 goals is to develop space solar power. And they have a tentative plan to go from ground-based demos to a low Earth orbit-based experiment over the next 4, 5, 6 years, depending on funding. And that awaits the decisions that Professor Kaya alluded to. There's an increasing level of interest and activity in China. A year ago, I would strongly disagree with anybody who tried to play the China scare card, i.e., oh, we need to worry about China and so on. But I have to say, in the last couple of months, last 3 months or so, there actually is a significant increase in the level of activity and interest and discussion. And there were discussions at a conference, as I understand it, in August, about the Chinese Academy for Space Technology actually pursuing a significant new budget for space solar power in their coming fiscal cycle. And there's ongoing interest in India. The biggest international collaboration discussion was the Academy study. And so that's been going on for the last 3-4 years, just wrapping up. And so the question is kind of what comes next. And that was the reason why I mentioned this one idea of this international working group to continue to foster the discussion and review and a body of knowledge concerning what's going on.
Question, was China part of the International Academy study?
No. Well, largely because their activity was mostly strictly in-country 4 years ago when the study got started in 2008, or it was originally proposed in 2007. There weren't any participants in the Academy study groups at a particularly strong level relating to these topics. So they didn't come. We organize at the International Astronautical Federation the annual international meeting on space solar power. And they would often propose papers, and we would accept their papers, but they never show up. This year, for the very first time, somebody showed up and made a presentation on Chinese activities. So it's just a phase change. But historically, we'd invite them, they'd submit abstracts, we'd accept them, and they wouldn't show up to give the papers. So there's actually been a significant... So we couldn't involve them if they don't show up.
Yeah, the Chinese program has deliberately been under the radar and more or less secret for quite a few years, and I think it really only came to light at this conference that we mentioned last August, first really open discussion of what they've been up to. And they have now reached a milestone in their program where they want to go to a substantially higher level of funding, and that proposal has been made to the Ministry of Industry in China, and the result of that is also under the radar at the present time. So, dealing with China,
Thanks, Frank.
it'd be very interesting, but it's more difficult than some of the other countries for a lot of obvious reasons. Yes, there's interest in the U.S. Defense Department. Indeed, in 2007, they did a fairly famous study at the National Space Security, or maybe it's the National Security Space Office, and there's been more talk since then. Most of this is not for public discussion. Peter, do you want to add anything from that? No.
I would just say that the sort of the general feeling with regard to this kind of activity is they would love to be customers. They would love it if this existed and they could buy energy from it, but they don't really want to be the first mover. And if there were to be a U.S. program, like perhaps a NASA-led program, if it got to the point that that was something that the U.S. pursued, almost certainly organizations within the Department of Defense would become engaged. And there are, at low levels, some research and development activities which are addressing key technologies for space solar power. One of them is managed by Paul Jaffe, who's here in the room from the Naval Research Laboratory, and he's managing a small project which is looking at the sandwich approach to microwave power transmission. So there's a level of interest, but there's a strong aversion to somehow getting, at this moment of significant uncertainty about future defense budgets, about somehow getting stuck with a new mandate. And there's also, I think, in a lot of the discussions I've had over the last year, there's a desire not to get in the middle of the development of what should be a commercial service, but to somehow be involved peripherally in that.
And let me emphasize the Department of Defense interest is not using this as a weapon, but using it as a source of energy.
Oh, no, absolutely, absolutely.
Is it a proof of concept?
The question is there interest at DARPA about this concept?
When we got started, it was Dr. Tether. So it's only been Dr. Dugan for a relatively short time, and so the answer is no, not at her level. But there have been working discussions with people in the relevant organizations in DARPA. And I will just say another side to this is, and the level of acceptance and interest and activity relating to this hypermodular approach as opposed to monolithic spacecraft systems or small sats in distributed applications, it's really shifting. You see a significant shift in this direction in a number of the way that different technical programs are being framed.
Question is the commercial sector, particularly energy suppliers, interested in supporting this concept?
At the moment, yes and no. There are some that are specifically interested. There are others that are watchful and kind of waiting to see what happens. I think that in general, the interest is not among any of the conventional utility operators per se, meaning none of them are going to undertake the development or they're not going to invest in space solar power. But again, they'd be willing to buy it. There was a very nice model in California with a space solar power startup called Solarin, probably premature, but the business model was get the major California utility, Pacific Gas and Electric, to sign a power purchase agreement to buy future space solar power and then use that as you go forward to try to develop the system. I think it was premature. It might, as we know from the technology assessment, these technologies are not just sitting there ready to build systems, but they're close and they're in the lab. So there's a gap of this valley of death in getting from the lab to the first proof in the field, and but there was no aversion because of the feed-in tariffs and because of the requirement in the state of California for that utility to provide more and more sustainable green energy sources. There was a willingness to sign a fairly major power purchase agreement. So as an expression of interest, it was significant. I think, but that's fairly unique. It was a really cool and interesting business model to pursue. But it's unlikely that utilities per se would have much interest in this.
Utilities in general in the United States are precluded from spending significant money on R&D. By the way, their business models are set up, which are regulated by the government. So they would be consumers of electricity no matter how it's produced, but they're not going to invest much R&D in it. Okay, that's a wrap. So thanks everybody for coming.